So we don't know what they're like. We want to take, and it makes a difference. If we want to go pluck a boulder off of an asteroid, it'd be nice to know that there was a boulder on the asteroid to be plucked. If you want to bring back a big rock, let's say if your goal is to pluck a boulder that's, oh, let's just say 10 meters across, weighing, thousands of tons, it'd be nice to know that that was out there before you went. If you spend an expensive harvester spacecraft to an asteroid to pluck off a boulder, and it's a monolith that's 100 meters across and there's no boulders to be plucked, you've just wasted your mission. So that's what the Fireflies are for, fundamentally. But we have another use for it. I'll get to that in a minute. The goal for the Fireflies are basically, we will plan on one price for a Firefly when you get 3 systems that we launch. The theory here is we are selling mission success. If we send 3, we're pretty sure that 1 or 2 of them will work. Because this is deep space, there's a lot of things that can go wrong, and we'd like to have some assurance of success. One of our philosophies, and we don't know what this number is exactly, we have different discussions in the company, but one of my philosophies is if we build 100 spacecraft, send them out, and 99% of them work, we've over-engineered. We have spent too much money on them, and we needed to probably do it cheaper and cut the cost in half, because everyone knows the 80-20 rule. 80% of your cost comes with the last 20% of your improvement, and that's just the way it is. And in space right now, the big companies have a focus where if everything has to succeed. So you build triple redundancy into it. You engineer out the wazoo, and everything has to work right. You get one test. You launch it. If the solar panels don't deploy, you're dead. If the thruster to move it out doesn't work, you're dead. Yeah. You spend $250,000 or $250 million or $500 million or more in some cases on some spacecraft. One thing fails, you're dead. We'd rather take an approach of doing things really cheaply in quantity, so that we can get mission success through redundancy, system-level redundancy. The next thing is the Dragonfly. The goal for the Dragonfly is to return 25 to 50 kilogram samples for scientific purposes. We know we can return them to high Earth orbit. We are looking into things like aero capture to return them to Earth via aero braking. But it's expensive in terms of delta V to get something from like the moon's orbit down to low Earth orbit where a Dragon or an International Space Station exists. That's a very expensive move, and so we don't. We're trying to find ways around that. Okay, harvesters. That's our name for our big systems that can return really large boulders. Really, so either really small asteroids or really large boulders on the asteroid. The amount we return with each of these is primarily limited by the return delta V. You grab this payload mass once you get there, and now you have to bring it back. If it takes a kilometer per second of delta V to bring it home, you can bring a lot less back than you can. But it requires 10 meters per second of delta V to bring it home. Then you can bring a whole lot back. This hundreds of tons figure for this is what the Keck mission proposed, and they were assuming 275 meters per second of delta V to bring an asteroid back. We think we might be able to find objects that can do better, but we don't know yet. I mentioned before, the communication satellites require fuel to maintain their position in geostationary orbit. And extending the life of one satellite for 4 to 6 months can be up to $40 million. there's currently also 40% of the mass of a current communication satellite to get it up there is fuel. It's propellant. And they have to lift that from Earth. It's expensive. They would much rather, they're not in the propellant business, they're in the communications business. They would much rather ship all communication satellite and have it moved and fueled in space. That would save them a lot, let them make a lot more money for the same amount of launch. Let's see. Anyway, we also believe that we would like to bring back asteroids to high Earth orbit so that NASA and astronauts can visit them there instead of having to go halfway to Mars to visit. It's a much safer, easier mission to just go to a Lagrange point than to go all the way to halfway to Mars. Another thing we want to do in the future, of course, is once we've developed the skills and to work on communication satellites and build communication platforms, we also believe in solar power satellites as a way to go, and that's a real target. We think that while some people believe in exporting high-value metals to Earth, we believe in exporting photons to Earth. That's where we're going to make money. Either smart photons in communication satellites, DirecTV, communication satellites, Sirius satellite radio, all those things. Those are all smart photons. They carry information. We also think that dumb photons, bulk heat producing, electricity generating photons are an important market. And it's potentially a huge market, and it eliminates the CO2 on Earth. Let's see. Fuel, of course. Okay. The early revenue we're aiming at is prospecting data and samples, tech development contracts with the government and others, corporate sponsorships, and of course planetary defense. The planetary defense is something new. This was not part of the announcement video because, hey, a little thing in Russia happened recently and got everyone interested in planetary defense. Yay! We have proposed to take our Fireflies and stage them in high Earth orbit, ready to go at a moment's notice, so that if we see an asteroid coming, when you first see an asteroid, you first detect it, it's at the limit of visibility. It's a barely perceptible pixel that's a little bit brighter than the things around it and moves. That's what you see. All you know is about where it is and about how bright it is. We don't know how big it is at all. We don't know what it's made of. We don't know if it's solid or rubble pile. We'd like to have Fireflies in orbit ready to go so that some scientist somewhere can say, this looks like an important thing. It might have a bullseye on the Earth. Let's go find out. So we trigger one of our Fireflies, we'll call them sentries for this application, and it will do a rapid flyby. It's all chemical propulsion probably, so it can respond quickly and get there quickly. And it'll go by and at least take pictures, maybe get a couple of spectral points so we can decide if it's carbonaceous or metallic or just ordinary stony, so we can see, if we can image it at 100 kilometers, we can see how many pixels across it is and measure it. We will know that it's 10 meters or 100 meters across or 300 meters across. And we will also be getting better information on its positioning, so that we will know precisely where it is going to hit. And then someone can make a decision, well, do we send some instruments to that area to take pictures, or do we have everyone step outside and away from their windows, or do we head for the hills? That's all things. Anyway, we proposed that we could do this, and it's something we're hoping to be able to do. We've got the systems on the way. I want to talk a little bit about Daniel's talk. Daniel is an expert on nanosats, basically the Cubesats, little tiny satellites. And we believe that the time is good for us to do the spacecraft miniaturization because there's a lot of companies producing parts for Cubesats. Basically, these are 10 centimeter by 10 centimeter units that do something useful. And it could be an entire satellite is 10 centimeters by 10 centimeters, not very big. But you can put them together in interesting ways and use some of them for propulsion, some of them for attitude control, some of them for communications. There's a standard processor block that's holds up to like 8 processor computer boards. You get cameras, all kinds of stuff is ready to go out there. And they are getting cheaper all the time, and there's better and more powerful tools all the time. Here's a picture of a Cubesat processing module. These are just off the shelf. You can buy these on the internet right now, and mix and match which processor things you want. You just have to add a little software, small matter of programming to put it all together. We want to also, as much as possible, use the latest technologies, the latest standards and protocols. One of the interesting things about Cubesats is the technology is evolving rapidly. This means we don't want to engineer something in now that won't fly for 5 years, because in 2 years something much better is going to come out, or at least much cheaper, and probably both, because Cubesats are undergoing the similar kind of expansion in powers and capabilities as Moore's Law. Well, it's not doing Moore's Law yet, but it's progressing, and it's an exciting field to be in. We do need to do some things differently. All the Cubesats out there now are designed for low Earth orbit, so we need to operate in deep space, so we will be re-engineering some of these things for deep space. We intend to develop technology, some things we return to Earth. The Firefly program this is what's called, we don't know that this will be, all this is speculative at the moment. What we've got diagrammed here is what's called a 6U Cubesat. There's 6 of those. It's basically 20 centimeters by 10 centimeters by 30 centimeters. And the solar panels fold out after launch. The antennas fold out after launch. It fits in a very tight, compact package. And it includes thrusters and things like that, so it can move on its own. We intend basically to demonstrate the capability and to do some imaging and learn a lot during these early flights. Our targets for the Firefly missions will be when things are approaching the Earth as closely as possible. We are looking at available sun-asteroid Firefly angles, because it's best if the sun is behind you when you're looking at the asteroid. We're looking for things at different asteroid sizes. Inclinations are important because it's hard to change inclination very much. It takes a lot of delta V. We have, however, identified about 5 targets per year, all the way out to 2020, from asteroids that we know right now. 4 minutes? No way. Okay. The Dragonfly Program is one that's going to return things. And it's going to go out, grab a chunk of rock, and bring it back. That's the theory. I mentioned that before. Our targets there are, the big question is return delta V, but we have at present identified at least 2 targets per year out to 2020. Beyond that, we're talking about bigger things, but we don't have these slides for that. That's the end of this presentation. However, I wanted to, you can turn the lights. I want to talk a little bit about my asteroid grabber. If people want to take a look, I've got a model here. This is the right size. Physically, this is the correct size for what's called a 12U Cubesat. It's 2 by 2 by 3 of the units. It's basically a little bit larger than 20 by 20 by 30 because for some reason these standards people think that 12 times 10 by 10 is basically 23 by 24 by 36. I don't know where they do their math, but this is the correct size. And the purpose of putting together this little model was to to see if we could get the mass estimate and volume estimate for how big the grabber mechanism happened to be, what kind of servos and gearing and mechanisms work. I came up with this one, which has some problems, but hey, it was built in my garage. It's not really a high quality machine shop. I have no capability of welding aluminum, for example, and my drill bit, my drilling skills aren't all that great, but it works. It's fairly easy to deploy. This thing in real life comes out, and if we take a little paper mache asteroid, this one would mass, would you believe, about 20 kilograms. They're heavier than ordinary
rocks. Can you do it on the table so we can see it?
Huh?
Can you do it on the table so we can see it better?
Well, I can try to do it on the table. Let's see.
Right here.
I also have to, I'll bring this over a little bit farther. Yeah, I have to apologize a little bit. My storage for these things, well, that's a little bit too far away, is, I guess that works. And it's really pretty simple. Let's see. Okay, this one's not working too well. I should. Okay.
There's no gravity up here.
There's no gravity, so it's easy. I've been trying some interesting things. These pads are real. My first attempt picks these things up really easily, but it has a terrible time picking up the big ones. And it's just a pad. And if I take these points that I was hoping to penetrate the paper mache, if I take these and bend them down so they don't penetrate, then we'll probably pick it up much easier. I destroyed one of my servos when I was building it. Didn't have an identical replacement and had to go